Okay, thank you very much, Roman, for the introductions. Uh, I'm a excuse me, I have a little cold recently, but don't worry, I wasn't in China lately. I came from a technical university of Denmark, and I worked there for more than 10 years, working on recrystallization phenomena, using both in situ 2D technique and 3D technique to study to watch what is happening locally. So as Mark told, with the 2D in situ TEM or EVSP, we can learn a lot of things. That we have a good high resolution characterizations, and the measurements can be relatively fast. But one of the drawback is that surface always have grooves, and it's not some problem with that is not representative because you have thin films. So especially for nucleations, when you cut it, you don't know maybe the nuclei already being removed. So due to these problems, about 20 and 25 years ago, and 3D techniques using high energy X-rays were developed. First family is 3D XRD, DCT, developed by former RISO group together with ERCF. So this technique now is still developing. And nowadays, the spatial resolution, yeah, it doesn't work. So here is the growing grains with a lot of, you can see that the grains is not spherical. There's a lot of protrusions and retrusions locally, and during its growth, it just continue this way. And with this technique, we can also map that the recrystallized grain itself is not perfect. It also contains some ultra-low angle boundaries. But with this kind of techniques, even we can have a good resolution like submicron and angular resolution like 0.005 degree. But we can only focus on the recrystallized grains. We don't know what the surrounding metrics. So at about the same time, there's another family of 3D techniques developed at APS, Advanced Photon Source, by Oxford Group and APS Group. So with this technique, it's called X-ray Lowy microdiffractions, and we can have voxelized-based crystal orientation informations. So here is a sketch showing the principles. So high intensity X-ray come from the angulators, and then focused with the KB mirrors down to the samples. One of the key of this technique is using the differential apertures to resolve that, X-ray was penetrating a lot. So using these apertures, we can get information in the depths. And this is a white beam, and with the detector, we can get a Lowy diffraction pattern and then index the crystallography orientations. So nowadays, with this technique, we can have a spatial resolution about 200 nanometers, and the angular resolution of 0.01 degree, quite typical, and the strain resolution of 1/10 to the minus 4. So lately we have also using this technique quite a lot. So this talk I will briefly show you what we can use this technique to study recrystallizations. So where we can have both the deformation metrics surrounding the nuclei. So we have both. So I call it full field, high resolution mappings. So I will show 3 studies quickly because due to the time limitations. The first is a nucleation study we did, and then the boundary migrations. And the last one is the residual stress in partially recrystallized samples. So for the first story is recrystallization nucleations. We use the pure aluminum to add the model materials. We roll it to 12%, and then we use a hardness to stimulate nuclei. This also will give us a good control of the nucleation behaviors. So here is the microstructure. Still doesn't work. None of the video works. Weird. Yeah, this projector doesn't like motion. Yeah. So we can see that under the hardness intent, there are a lot of color changing. That's the orientation change due to the focus, due to the load. And beyond that, is a relatively regular deformed microstructures. And after 275-degree annealing for 10 minutes, and we see some nuclei. Most of them are come at the indentation tip. And if we just look at the nuclei, yeah, they are just below the indentation surface and clustered around this indentation tip. And in total, we found 12 nuclei. They are not so big, so they are not growing out of the gauge volumes, and so we can still analyze a lot of details. And 2 of them are twin, and one is growing too large, so we didn't analyze that. So we have 9 nuclei to analyze. So with this kind of data set, we have the deformation matrix before the annealing. So we can correlate the orientation of the recrystallized grain to its consumed deformation matrix. So here the color means misorientation deviation from the recrystallized nuclei. So more hot means more misorientations. So in this volume, we found that a small volume that contains 3 voxels, which have an orientation close to the recrystallized grains. So therefore, we believe this is where the nuclei was formed during the annealings. And in that way, so we can quantify all the nucleation site. This movie doesn't work either. And what we found that most of the nuclei have born within 2-3 voxels, and they are aligned close to the indentation diagonal lines. Since we have the orientation before we anneal it, so we can analyze the form microstructure in details. So here is the calculation of stored energy. This stored energy means that the energy is stored in the dislocation boundaries. So any foreign dislocations or elastic contribution was not included. This also will be very small compared to the energy stored in the plastic deformation boundaries. And the cross marks where the nuclei come from. And if we look into details, so here is one nuclei and several of them here. So what do we observe that most of the nuclei come from a place where the stored energy was relatively high. But we can also see that not all the high stored energy stimulate nuclei. It's only a few of them. And we can also analyze the statistically what the boundaries that moves during the nucleation process. So here is the nuclei and its corresponding consumed volumes. So if we calculate the misorientation between this and this, that's equivalent to all the boundaries that's when the nuclei growing, consuming the deformation matrix. And what we found that a large fraction of boundary have high boundaries with misorientation higher than 10 degrees. And we can also see that for the 3 largest and the 3 smallest and 2 largest, there is a difference with misorientation angle below 5 degrees. So we believe that high angle boundaries with misorientation higher than 10 degrees are good for the nuclei growth, and below 5 degrees have some hinder effect. Here is a short summary. So with this technique now we can really observe in situ what's the nucleation process and pinpoint some nucleation mechanisms. The nucleation is stimulated at the high stored energy regions and have orientation already present in the matrix. And the boundaries with the misorientation higher than 10 degrees are good for the nucleation, and less than 5 degrees are probably hinder the growth. After that, of course, we also want to follow once a nuclei is born, how it grows and migrating, consuming the deformation matrix. And then we conduct second experiments to follow the boundary migrations. And using this technique, we choose recrystallized boundaries in a pure aluminum after deformation, 50% core rolling, and then 250-degree annealings. So you can see that green part is a recrystallized grain, and here we have orientation variations, that's the deformation matrix. And we can separate them and look into details of the boundaries. So here the movie doesn't, oh, this works. Good. Suddenly. Yeah. So if we remove like your transparent to see the recrystallized grains, then you can see details of the boundary plans. But if we see this again, take a good close view, so we see the boundary is not not uniform. It's contain the staircase, some facet and some curved part and facet again. So this is on a scale of 10, 20 microns, so it's not an atomic scale of facet. And the bond contains some, this is a mark where the facets are, and those are the curved part connecting the facet. And after annealing, so you can see that the deformed grain has been consumed. If I flip again. So that means the boundary is migrating and consume the deformation matrix. And by correlating the two boundary positions, we can quantify how much each pixel voxels move during this process. And we can clearly see there's a lot of hot voxels move about 10 microns, and the facet doesn't move much. Expect here, but this is the motion in connection to the curved part. So since we have detailed data on the deformation matrix, so we can analyze why this part moves faster than this part. And the first possibility we can think is that the driving force will normally determine the migration velocity could be different for the facet and the curved part. And we did some calculations for the facet. We call it a non-moving part, and the curved part is moving part. So actually, we didn't find that much differences. Indeed, non-moving ones have a little lower cell energies, but the fraction is not that much. For both steps, it's consistent. And we can also quantify the misorientation for the moving and non-moving boundaries. And surprisingly, for both annealing steps, the moving ones and non-moving ones, they are very similar for the misorientations. So the rotation axis, also the misorientation angles, also between different steps. So there is no much difference between the moving one and non-moving ones. The only difference we can see that is the boundary plane normal is different. Of course, for a facet, we will have a sharp peak here, but the diffuse cloud is from the curved part. But is it that's the really reason for that slow motion? So to answer this, we did some MD simulations. So we select a boundary with the misorientation close to our recrystallization boundaries and have a normal one close to here and two in the cloud. And with these simulations, MD simulations, what we conclude that the boundary one, which is doesn't move, have a mobility is almost the same order of the other two, sometimes even higher, but that's the best we can get. This clearly indicates that the mobility of this boundary plane normal is not significantly lower than the others. This also makes sense because if a boundary moves much faster, and they have a typically maybe low Miller index, that's we can understand. But now it's the opposite. We have only one normal doesn't move, but the rest is moving. So therefore, we believe this, even this MD simulation, we believe this is actually a good reason that this boundary is nothing special for compared to the rest. But what else we could think? Why this part just doesn't move that much during the recrystallization. Let's look at the boundary again. Now we color the boundary according to the cell energy and the misorientation rotation axis, which means between the recrystallized grain to each voxels, the misorientation rotation axis. So we see that a mixture color for both the facet and the curve part. This is agree with the average informations. Also here, the color is quite mixed. But if we put the boundary trees on top of the deformation areas, we see that the boundaries move mainly along these directions. And in these directions, we also see some band structures. So if we draw a sketch to represent these deformation macrostructures, we see that there is actually two sets of boundaries, and one have a higher misorientation angles. And that one is clearly have a dominating effect on the boundary migrations. Even though the store energies, misorientation is the same, this have an extra impact on the boundary migrations. We have also show similar behavior from 2D EVSP and another 3D studies. A short summary says with these techniques we can get details about boundary migrations. So we can analyze details of boundary migration velocities and the driving force and the boundary plan normal and misorientations. One important conclusion we have is that the local geometrical organizations of the dislocation boundaries play an important role from the boundary migrations. So this is the conclusions, but what is the physical reason behind this we could think of? We know that when you have dislocation boundaries, the dislocations can generate a strain field around it. And this different organization clearly means different stress field. Is there a really stress field in the for these recrystallization boundaries? That's leading to our third stories. So we try to quantify whether there is a residual stress in the recrystallized grains. So come back to this technique again. Now we also insert monochromators. So we change the polychromatic beam into the monochromatic beam. In that way, we can map the lattice parameters and get the strain stress informations. We use Amco iron as a model materials, and we roll it to 50% and 90%, and then we anneal at the different temperatures to get partially recrystallized microstructures. And these two, we have a 50% cold rolled, 550-degree annealing at 10 minutes and 30 minutes, and we have a parameter as function of different volume fraction of recrystallizations. And this one we have a 90% cold rolled and annealing at 500 degrees for 30 minutes. We compare these two, we have a similar amount of partially recrystallizations, but we have a microscopic strain is a difference. Also, the sample has been cooled, one side by water quench, one side by air cooling. And this is one typical strain mapping. So using this technique, we can map the strain within the recrystallized grains, and the strain component is along the RD direction of the samples. And this, we can see that the strain is not uniform everywhere, not within the recrystallized grain, between the recrystallized grains, and the strain can be higher in the middle or can be higher at the grain boundaries. So there's no clear correlation why these strain are distributed in such way. And if we look statistically, we see that for the water quenched samples, they're relatively higher residual strain in the order of 10 to the -3 for both samples. And compared to the air cooling ones, the maximum is around 5 times 10 to the -4. And the variation between these three is not that high. So the dominating factor is the cooling rate. And between these two, the volume fractions have a less impact. Between these two, the external stream have a less impact. Oops, why doesn't this one? Ah, it's freezing. Weird.